So today I'm going to tell you a bit about what Sperry Rail do. I'm then going to tell you a bit about what my team of data scientists, DevOps, big data, cloud specialists do to support Sperry Rail. And then I'll obviously be saying how we use AWS and how AWS supports the work that we do. So, I'm Senior Director, Digital Transformation. So I've got a lot of background in railways, because the clue, Sperry Rail, we work on railway stuff. My background's in mathematics, and I've always worked in modelling, more recently AI, embedded system development. I'm also going to mention our founder, so Mr. Sperry, his name Elmer Sperry. He was our founder. At one point, he had more patents than Thomas Edison. And one little thing he did towards the end of his career was come up with a way of finding cracks in rails. So we've actually called our artificial intelligence platform, we've named it after him. So if you hear me talking about Elmer, that's actually our AI system, but it's named after our founder. So what does Sperry do? We have a fleet of vehicles all over the world, and we look for cracks in rails. We do the whole of the UK, and lots of North America, and well, all over the world. What are we looking for? So this diagram here, there are lots of ways that a rail can get cracks in. Now, some are more historical. They're manufacturing things that can happen that modern processors don't tend to produce, but there are rails out there over 100 years old, so we have to find all sorts, and others are rolling contact fatigue. You see RCF up there is, there we go. That's a more modern thing, typically comes from high-speed trains. So as you can see, there's lots and lots of different cracks in there that can happen. There are also things in there that are supposed to be there, like where there are bolt holes, where there are rail ends, where there are welds. And we have to try and detect all these things and sort out the bad from the good. So we have a number of technologies to detect it. Our main one is ultrasound. So we have ultrasound systems, just like they use in medicine. I think we run at a slightly different frequency, but we couple it onto the railhead, and we whiz along, pinging it and looking for echoes. We have some other systems based on eddy current, induction, vision, obviously. You'll have to refer back to your A-level physics, but basically they're different ways of putting signals, magnetism, etc. into the rail, and we see where there's a variation from the norm. Could that be caused by a crack in the rail? This is an example of the actual technology set up. This is actually on a road rail vehicle. You can just see the tyres there in the background of this vehicle that can run onto the rail and run along there. In the UK, Europe, they're mostly adapted rail vehicles. In North America, they're mostly road railers. So you can see, I'll find the mouse. There we go. So these funny, they're sort of like water balloons, really. They're full of water and sensors, and we also squirt water on as couplant onto the rail, so we can ping through and get our ultrasound detection. So, and there's vision systems there and all sorts. So that's what it looks like. What are we looking for? Well, here are examples of an ultrasound response. So imagine this is like a side view of a rail. So you can imagine the rail head is there. This is the rail web. This is the rail foot. A bolt hole, that's the sort of response we get from a bolt hole. Here's an example of a bolt hole there. This one's actually got a crack in it. Normally it would look like typically like this sort of A shape with the red, white and blue there. But we've got this bit of red sticking out that shouldn't be there. And that's because of this crack that was forming there. When this rail was removed, sometimes we break them open to just check what was really there. So you can see that was the growing crack, and the grey stuff is where it was broken. Now, eventually it will break itself, so we've got to get there first. Here's another example. Here's one that's a crack that's crept in from the head. Again, you can see where it was growing when the rail was broken open. You can see that's getting pretty dangerous. That's not far off. If it got, I don't know, as big again, you get a catastrophic failure, the rail breaks. And our ultrasound is picking that up. All the different colours, I think we've got about 14 different transducers. They're all looking for echoes, and that shows up in different colours. So we have a team of analysts who look through these scans. It's very similar to medical scans, really, only you have X-rays, MRI, you have ultrasound, obviously. You might be looking for broken bones, you might be looking for cancer, you might be looking for something else. Very intensive trying to sort it out. And just as in medicine, there's a whole load of AI developing to try and do the majority of that scanning and then pass on the things that turn up of interest to the experts. Because there's lots of stuff we have to weed out, as you'll see. So what we've been doing is developing neural networks. Now, some of you may have worked with neural networks, AI, but this is a one-slide course in how neural networks work. Basically, you've got a big network of, it's a mathematical thing. Think of it as a table with connections, and you have inputs coming in here. If it's an image, which our ultrasound is effectively an image, these might be pixel values in the image. So you might have several hundred pixel values coming into the first row. And depending on the values, they might pass something through to the next row and the next row and so on. And eventually it all boils down to, is it one of these or is it one of those? Might be, are we looking for pictures of a cat? Is it a cat? Yes, no. And you train it, to begin with, it's all set to random values, doesn't really know anything. And we feed it through and we say, is it the thing we're looking for or not? Is it a crack? Is it not a crack? And of course it's got no idea, so it guesses. And maybe it gets it right, maybe it doesn't. But of course, we've got lots of training data, so we know what the correct answer is. There's some very clever and complicated mathematics that works out how to, it looks at what the answer it got, it looks at the answer it should have got, and it adjusts all of these values to make it just slightly more likely that next time it will get it right. And then by the time you've shown it thousands of values, it's getting pretty good. And by then, you test it on data that it doesn't know the answer for, that it's not seen before, and if it's looking good there, we can start using it as a tool to predict. So we're no longer testing it, we're assuming it knows what it's talking about. Clearly, we do a lot of validation there before we get to that point. So that's your neural network. What neural networks have we got? Well, we can feed in our ultrasound information, and also from our other systems. I'll concentrate on the ultrasound today. We've got various convolutional neural networks, and what we're trying to get out at the end is what sort of feature is it. So let's say we're looking for bolt hole cracks. So we might feed in scans here, and we're saying, well, is it a bolt hole crack? Is it just a normal bolt hole? Is it a bond pin, which looks a bit like a bolt hole? Or is it none of above? And we train it to do that. Here's some examples of training data. So top left, that's a fairly good quality typical scan. These blue stripes here show that it's recognized it several times because we sort of feed the data through a window step by step. And as it's passed through the window, it's said several times, yep, that's a bolt hole. And as you can see, there's lots of different combinations. We don't always, our transducers don't always get a really good signal. Sometimes there's bits missing. But all these different things, we would expect that there's noise sometimes for it to say, yep, that's all right, I'm confident with that, that's a bolt. And then we also show bolt hole cracks so that it can tell the difference. And the difference is all these little bits that are sticking out, they're signs, and just there, that it's a crack. In fact, there we go, I've marked them all. And these green stripes here, it's just a diagnostic. Interesting there, to begin with, as it came through, it said, oh yeah, pretty sure that's a bolt hole. Correct, very good. But then as it gets more information, it goes, but it's a bolt hole crack. So that's good. So that's how we train them. We also show it things that might confuse it. So you can see top right here, sometimes these bolt holes get drilled very close together. That's bad practice, shouldn't happen, but it happens. And you can see where they're overlapping here. If you just ignored that bit on the right, that starts to look a bit like a crack in the previous image. So we have to give it more information and show it, it's all right, don't cry wolf, these are okay. This was an interesting one. It was all working fine, and then we went on one rail network, and it started throwing out you've got bolt hole cracks all over the place. And they all looked slightly different. And well, we call them space invaders, because anyone who's old enough to remember, that's what space invaders look like. And it turned out they were a particular bond pin that they welded on the rail, and it had a signature like this. We trained it up. We only had to give it about 100 of those, and suddenly it goes, oh, OK, not a bolt hole crack. Know where I am. So that's how neural networks work. You show them lots of stuff, and eventually you believe they learn, but they're very sly. They will find the easiest way to learn as possible. So if it was a game of cards, if they can memorize the deck, they will memorize the deck rather than learning the rules of poker or whatever. So you do have to do a lot of testing. There's a classic one, neural network, can it tell the difference between a dog and a wolf? And they trained it, it got really good. That's a dog, that's a wolf, that's a dog, that's a wolf. They looked into it a bit more, and it turned out all the pictures with wolves in had got snow in the background, and all the pictures with dogs in hadn't. It was actually telling the difference between snow and no snow. And they only worked that out when they showed it data from a completely different source. So you have to be very careful. Right, so that's how we trained up our neural network. Having got it going, we've got to then put a pipeline together to make this useful for the analysts who are actually looking for stuff. And this is where AWS starts to come in. So I've got a little video, which if we're lucky, we'll get sound as well. It's very short, and there's a lot going on. But basically, you'll get a view of what the analysts see. And they sit there looking at this screen, and there's data flashing by on this screen. And we try to, historically, we try to weed out the stuff that is not of interest to them and just stop on things that we need a view on. But there's a huge amount of stuff, traditionally, that we need them to make a decision on. With the neural networks, we've reduced that hugely. So what you'll see, there's a voiceover, but I'll just give you an overview so you know what's going to happen. You'll see this viewer screen, there's a top rail and a bottom rail, and you'll see data coming across quite fast, and every now and then you'll see something that's marked, and they go through it a right old lick. They go really fast to find things, because otherwise they just won't get through it all. When something's marked, they can choose to click on it and say, yep, I agree, that is a flaw, or no, it's not, that's false positive, carry on. And then in this voiceover, we just pause it, we sort of go under the bonnet, and we show you how Elmer works. If the sound works, I'll just stand back for about 45 seconds and let it take you there. If it doesn't, I'll have to try and talk quickly over it. So let's see, here we go.
Normally, an analyst would just see the results of Elmer's final decision about where there is a flaw. But with this display we're looking at now, we can look at the decision-making process. Elmer has marked along the bottom margin with coloured stripes what it's recognised in the ultrasound hits above. The height of these stripes shows Elmer's confidence that it recognises what it sees. Here, it's hunting for bolt hole cracks. As I click on the stripes, Elmer shows the details of whether it has detected a bolt hole crack, a normal bolt, a double drill, or an item that's not of interest for this particular neural network. The voting process decides what information to pass on as the final decision, and this is what the analyst will see.
So, I think the analysts get about 6 month training course. You've just had it in 45 seconds. So there we go, that's what they do. Right, so I'll move on. So I'm just going to go through a bit of a timeline here of how we develop stuff, and this is where we'll start talking about how the AWS, the AI, all that sort of thing comes in. So back in the late 90s, Sperry sponsored some university projects to develop neural network recognizers, and for the time, they were sort of successful, but the speed of processing and the availability of data, I mean, neural networks back then, just not really practical. So it was sort of an okay start, but didn't really get anywhere and just went quiet for 16 years. And then the Sperry Innovation team was founded. So initially, that was me. We now have a team of 8 or 9 or possibly 20 if you count the partners we work with, who include Steamhouse, who are here, and iTechArt, who they help us with Steamhouse with the cloud stuff, iTechArt with other things. So in one way, we're an in-house team of 8 or 9, and we're a wider team of about 20. You can see us there working during lockdown with various levels of facial hair coming and going. I've actually got, there's some people, with some new people. There's some people here today from that team. In fact, they're on the front row. In fact, just stand up, guys. Turn around. These are the people during the coffee break. If you've got any questions, grab them. They might have a Sperry logo on. So if you want to know more, we'll probably have time for questions anyway. But if not, grab one of those guys. And so there we are, all working during lockdown. Back in 2018, we got the bolt hole crack detection working and had this idea of calling rather than the AI system, calling it Elmer. It was quite good, giving it a personality. People related to that say, oh, Elmer's really good at this, but Elmer's really stupid at that, you know. So it just helped you, yeah. 2019, TDs, transverse defects, they're these ones that come in from the side. We got it recognising those. And this was, right, we're getting into the AWS stuff now. So this was, as soon as we started doing this, the analysts were like, well, how can we see this? And the first versions, in fact, the ones we still use, we don't have any front end for this. We produce an XML-based report, and it looks like an analyst has had a bit of a go at the data, and they can import this into their viewer, and it's like their assistant has had a first go at it, and they they carry on from there. So we didn't have to produce any front ends. We just have to produce this report. So we put this pipeline together. This was round about when I suddenly realised I needed more people in the team. I think I sort of got most of this together, but it was when Abel and Wade joined that we got it to work properly. So we're getting data is being uploaded from the field to our servers. We wrote a little bit of code to move it from the servers into an S3 bucket. We've got lambdas triggering things. So when something arrives, new data in these files, T1K files, we trigger it. If it's on the whitelist, we pass the data, generate run files, put it in a queue, and then we push items from the queue into EC2 processors. Every run, we run 3 neural networks on it at the moment, so we have to run 3 things in the queue. And when it's run through that, we upload the results. We've got these multiple results from the many neural networks, so we have to combine them, so we don't report things multiple times. So we come up with a final result in an S3 bucket, and then we FTP that across to where our analysts can find it. And there's then a secondary process where we're watching when the analysts do it. They then go through and they go, no, don't agree, yes, agree, don't agree. So we effectively, we're getting more sort of ground truth. There's a second step with verification as well, but closer to ground truth. So we had a learning pipeline as well. And you can see there's a lambda here. We're uploading the results from the analysts, so we'll get those a few hours later. And this is checking, and once we've got results both from the analysts and from Elmer, we compare them, more EC2 work, and we say, well, the ones that agreed are true positives, the ones that disagreed, false positives, the one we missed are false negatives, and we put that into a learning bucket, and then every now and then we can retrain Elmer and go around that loop. So that was working really well. Trouble was, as soon as we were finding the bolt hole cracks, and particularly when we started finding the transverse defects, which are A, more common, and B, more dangerous, they can go bad faster, they're like, right, we want it, please, you know, right, you've been doing like 2% of what we want, can we have 100%? Oh, no, how about 10%? Well, okay. And what we got, what this is basically, red is queuing. That's the main thing you need to know from this graph. And we're getting data coming in. There's 2 ways of looking at the same data. We've got data coming in throughout the day, and every time a new run arrives, it kicks off, starts queuing in red, gets analysed, which is amber, yellow, and then when it's delivered results, that's blue. And you can see they're all nicely bunched up here, but then it can't keep up. And then it falls behind, and then it falls further behind. And you can see on average, we're taking over 3 hours on average. I mean, these early ones are really quick. But down here, you can see some of them are taking 8 hours to process because they're just sitting in this big queue. And we were firing up EC2s, 10 or even 20, I don't know. But victims of our own success. So that point, we did a well-architected review with Steamhouse, and that was really useful. But amongst other things, we came up with some follow-on work, and one of the things that did was turn this into a serverless system. So now, I've got a Bell who's going to talk later, or answer questions. He's going to answer the really difficult ones. But he's annotated this for me. So basically, everything from here on is step functions. So we don't need a queue. And rather than using EC2s, we're now using we'd always put them in containers, so that was handy. So it was easy to drop them into Fargate and use containers. So now there's no limit. We can run hundreds in parallel. And that previous graph is now looking, everything comes in, gets processed. On average, it's taken about 30 minutes. We're coming up with ways to speed that up, but that's okay. The analysts, most of the stuff, you can see there's the analyst shift. Well, they've got to work through all this lot that's all ready for them. By the time they get into the end of the shift, they might be getting a little bit, come on, guys, where's this stuff coming? So that was our first iteration, well, first and second iteration of AWS. How are we doing for time? Oh, we've got 15 minutes left, that's right. So moving forward, AI, machine learning, just feeds off data. And I'm sure everybody in this room probably has something to do with programming software and knows the importance of version control and repositories and being able to do comparisons and know what you did last week and what 3 lines of code did you change from last week that mean it didn't work anymore, all that version control. As soon as you get into AI and involve data, you are in a higher order of magnitude of the same thing. Because not only have you got all your code to consider, what data did you train it on? What data did you verify on? What data have you run it on today? What combinations of results gave you your final result? Was it just one neural network or 2 of them? And you will get into a mess so quickly. You'll see there's lots of nice demos of how you can build a neural network. And just like you see demos of knocking up a bit of software to give a front end, you think, oh, that's marvelous, that's great. They did that in 10 minutes. I can be a programmer. And you get into it, you realize professional programming is harder. Same with this. You can knock up a neural network, you can train it, yeah, that's brilliant. But then you retrain it, and you retrain it, and then you want it to take account of something else and something else. And you have to be so on top of it not to get in a really, really tangled mess. And we realized the result of this, the requirement that we needed was big data, a data lake, and all sorts of, I'd say, probably 3/4 of the software we build is all to do with managing things. So we built this cloud. So the process now, we're uploading data. It's going into what we call our big data lake. And we're actually calling it Zula, because Elmer Sperry's wife was called Zula. What a great name. Obviously, back then in the must have been end of the 19th century, already thinking of names that would be good for software. So we call the big data lake Zula, and we call the processing Elmer. So that's all in the AWS cloud. We're using TensorFlow and similar AI-type tools, all running in the cloud as well. And because we've got everything in the cloud, now all the data we've got, it's all there. We're no longer using individual big chunky binary files. Well, we do, but we pass them into the cloud. And from that point on, we've got every single echo that we get on the railway anywhere in the world. So all of last night will have been loaded up. Every single one of those echoes will be a line in a database somewhere. And that's allowed us to do lots of things. One example of that is this pinpoint synchronization thing we've got. And because one of the things, you can get far more interest if you know what was there last time. So you've recorded it, what was there last time? And you think, well, that's pretty easy, isn't it? Why don't we just sort of compare it to the last recording? But the last recording, well, when was it? Was it exactly, did it start and finish in the same place? Probably not. It's a bit like saying, I want to compare what was said in this room this week with last week. And we recorded last week, we recorded this week. But how are you going to synchronize it all, yeah? And it's very complicated. But we've come up with a way that does that totally automatically. We've got any cyclists in the room? Anyone use Strava? Yeah? Yeah, we've got a few. So Strava records all your GPS data if you go cycling and various other things. And that black circle, I'll get the mouse over there, where's it gone? Is, well, you see that black circle roaming around. That's me cycling around the Peak District. And you can see various other people. It just shows you people that are passed in the Peak District. So we use that idea to, whenever we record something, we put it through this, what we call flyby process. borrowed the name from Strava, and it shows other runs that were on the same track or the same line. They weren't necessarily, they might have been on the adjacent track. And then we have this process that I'm showing pictorially at the bottom. There's a mouse. And it's comparing things that the neural network has found. And this bottom one, it's top and bottom, as show often there's nothing there for long periods, but there's quite a good agreement. And so this thing here is green. Can you see the green percentage thing? That's basically saying, I believe that's the same run. Here, this one, it's not the same track. That's mostly red. We've got poor agreement. With that, we get pinpoint synchronization. It's incredible. The GPS will get us to a few meters, but this will get us down to millimeter. So there's an example here. The top run is one we recorded. In blue, it's just a diagrammatic thing of 10 miles of track, and it's saying those two red runs underneath, whilst they were on the same route, they weren't the same line, so we throw those out, whereas the three green ones underneath that were done over a couple of days match perfectly, so we know how to match things. So the result of that is we can look at two runs side by side. The one on the left is the previous run a few months ago. The one on the right is today's run. And, well, you've all been trained in ultrasound analysis in that 45-second thing earlier, so you'll be able to see that there's just a tiny little blip there that shouldn't be there and wasn't there last time. So that's been marked as a bolt hole crack. And then there's this big thing here where last time there was sort of something, but there was a lot of contamination on the railhead, so it wasn't picked up ever so well. Whereas now it's saying that's very much looking like a transverse defect. These two images are synchronized side by side through the run. GPS gave this a 6 meter difference, but well, by eye, you can do those bolt holes, that's a whole string of bolt holes. They're about 20 mil wide, and it's pretty well bang on. 2022, we got the AI working for all of the things all of those different cracks I showed you in the early slides. That's all. So we moved across to Elmer AI. This is just basically the top graph showing we're getting nearer and nearer to 100%, and the bottom one's showing the number of recognitions we get. They are increasing, but at worst, they're a third of what we used to get with the old system. We've developed systems that using other technology, eddy current technology, to find other features in the track. They're being developed. And at the moment, the big push is, I said there was no front end. And the old system that you saw a little bit of, well, we wanted to design a system to replace it. So we've got storyboards here. That was that old one I showed you, side by side. And anyone who's ever used that will lovingly tell you that they hate it. It's clunky, it falls over, it takes you ages to load the data in. So we're replacing that bottom up. First thing, all of it is completely data driven. The old system, you had to find this file, that file, is this the one matching that, put it in, all this sort of thing, get it into the right folder. Whereas this, all data driven, so you have a front end. This is the design of it. This bit is actually working now in prototype, and it pulls all its data down from our big... So these are all list of runs, and it's saying, well, what's been analysed, what's still being pre-processed by Elmer. Has an auditor looked at it? If you're an auditor, you go into one of those and click, say, right, I'll have a look at that one. And now we've got this more sophisticated viewer. So again, we've got the two rails side by side, but we actually show a history of everything that was found in the past. So these icons here are saying, right, that looks like perhaps a bolt hole crack that's starting to go through the head, and there's an icon for it. Last time that was shown as well, whereas the time before it wasn't, and it looks like it's growing. Likewise, there's something here, and so you can see what's changed. We've linked it into Google Maps type view, so I can see it's near a level crossing. There's a bridge just to the right of it. It's on a curved bit of track. Level crossings and bridges are higher risk, so we're putting all of that together, and then taking all this historic data that we've automatically synced with the process I said earlier. We've got this thing. People who are into ultrasound, you have A scans, B scans. I believe there's a C scan. Well, we've invented a T scan. It's time-based. And this is actually 10 miles of track for each rail. And all these, this is the prototype, so it's not ever so legible. But you can sort of see the patterns here. And one thing that jumps out is this most recent run. There's a lot of orange stuff going on there that wasn't there before. And so our data collection people can look in there. Is that because the system's tuned poorly and needs setting up? So putting all this together, it can help the analysts with the detection. It can help the people in the field. Right. Just got to my last slide here, which is the AWS architecture, the bit you're all interested in. So this is what we're building. So we've got this fully data-driven system. We've got this is Zula, the big data system. We're using a number of technologies that I'll come on to in a moment, but basically we pull it into a big, slowish thing. We've got a faster cache, and we've got management going on. This is all linked to the processing, so any processing, all step functions and containers can be triggered by time as well. Any extra value we get gets pushed back into the big data, and then we're developing all these different viewers. I showed you a couple of them. There's various others and aimed at other things, and then different users. So the analyst wants to look at it, the auditor. My guy's here, Rusbe, who's sat here, and he's training new data. He will look at that data in a different way. So those are the technologies that are in that slide. Got 5 minutes left. Any question? In fact, a bell. Why don't you start? I'm going to have a bell stand on the stage with me, because if you want to ask really probing questions about AWS technologies, I'm going to hand over to a bell. If you want to know about maths or AI or whatever, I'll answer. If that gets really hard, I'll tell you to talk to Rusbe in the interview. So any questions on all of that? Come on, don't be shy.
I have a microphone. Is it working? Yes.
Yes, one over there.
I saw him first. Hello, Tom.
Hi, I was just wondering how you dealt with the feedback from your end users, because obviously you were completely changing how they were working from the old side-by-side view of the interface to this new whiz-bang one.
Yeah, so the old side-by-side one has only been in there for a year, because we made that possible with the sync, and so they love that because they can see things straight away, but they're driven mad because their eyes are jumping all over the place. They end up with 7 windows open. We work closely with them on prototyping the new one. To begin with, they're like, oh, what's that? That's weird. I don't understand it. It doesn't make sense. And as we talked it through, they started inputting and tweaking things. I think it's fair to say they're really excited about it. Now, we've not yet got to a point where we've got a prototype on that, but yeah, they're sort of highly suspicious because, old management are chucking some more software on us, but they're now, well, I'll believe it when I see it, but it looks fantastic, is what we're hearing.
There was another one here, wasn't there? Yes.
What kind of benefit are you seeing in terms of performance time? So the analysts bringing in AI, how has it improved your overall kind of work?
Yeah, well, that's a good question. So just putting in that syncing process halved the time it took. So we got a 2 times increase because they're not trying to line things up by eye and find stuff, and half the time they don't bother unless it's a really weird-looking one because they just haven't got time. So that increased. That was a 2-fold increase. We're predicting at least another 2-fold increase with the new viewer. Along the way, the number of we sort of test ourselves. Whenever we find a large flaw, we go back in history and say, well, what was there last time? And if there's something there last time that really we should have found, maybe it was borderline, yeah? Well, we that's a bad mark, yeah? And that has already, the number of those that happened have already gone down by, I think it's some factor about 6. I was talking to the analysis guy last week, and we feel, the target there is to get that down to 0, and I think we might get there. 0 on a good year, a few on a bad year, so quality going up really well as well. So, yeah, partly because the systems there, they're distinctly legacy systems. There's quite a lot to gain there, but we've already seen probably a 2+ increase in turnover and a 5 or 6 increase in reduction in quality slips.
Any more? Oh, loads. I'll have to walk quick.
Yeah, thank you for that. Are you looking, with the AI to kind of ultimately have all of the intelligence in the system, so the analysts don't need to be trained up for 6 months to be able to do that, or ultimately looking to kind of get rid of the analysts? I was trying to think of a nice way to say it, but ultimately.
Yeah, just keep your voice down. No, that would be, ultimately, you could approach that point, and steps along the way is finding the really obvious ones, taking a skim off the top, send them straight out for verification without the analysts, and then as they get more tricky, I think we will get to a point, A, where we get those, and B, where the analyst's role changes and they become trainers and auditors of the AI, and maybe in 5 years' time, the AI is largely doing its job by itself, and the analysts are now, rather than being under time pressure to get it, that they're now more stepping back and saying, let's just check, what does it need more training in, that sort of thing. Has anyone got a difficult question on AWS for Abel before? Because we've just probably only got one more question, have we? Any tricky? If not, you'll have to grab him in the interval.
I've got one very quick question. Unfortunately, it's not much of a technical question. Apologies for that. And I think really it's a two-part question. So there's a bit of a silly question at the beginning, which will lead me to my second one. So my first question, I take it this is all part of a predictive maintenance project of some type with Sperry. Would that be the case?
Yes. So the railways have programs of replacing rails, of grinding the top off rails, of milling the top off rails, of replacing short sections of rails where there's a fault, because what you don't want is broken rails. Anyone who remembers Hatfield from about 20 years ago? That was a result of not detecting things, the whole maintenance regime. So it's to guide that. It costs about £1 million a mile to replace rails, so you don't want to do it if you don't have to, but if you don't, the consequences are a lot worse.
And that was leading to my second question. So is it a case now that it's reducing costs and perhaps even reducing resources for Sperry now?
Our bit, we work with the actual railway companies themselves, and we tend to get to the point of the verification to say whether it's there or not. But we develop wider tools. We have a whole suite of things that we call Rail Health, and that is to do exactly that. That's to tie in with their maintenance regime and things like, well, rather than replacing 6 meters here, why not replace half a mile, because there's a history here. And again, the big data helps show, right, you've got a history, this curve has got, just replace the whole thing makes more economic sense. So yeah, working with them on that.
Excellent. I just wanted to very quickly say, by the way, it was a very interesting presentation. I thought it was a very good presentation, Bobby. Thank you.
Thank you. Oh, we've got one at the front. There's a question at the front here.
Right. We'll have to be super quick. Is this a question for Abel? Yeah. Excellent.
So do you see any limitation in the AWS, like getting the data and then doing everything on cloud, basically, based on all the architecture that you have? Do you see any limitation, or is it just faster, better?
I think the only limitation is the manpower you have to be able to implement all the different services that could help you detect things faster, like implement, streaming, multi-processing, like doing multiple jobs at the same time, or splitting the one big run into multiple ones so you could give the analyst results faster. So yeah, the only limitation you'll have on AWS is like having people to implement all of them, but like there isn't anything. Yeah, that's why we use Teamhouse.
So limited only by our imagination and the time to implement it then, is that?
Exactly, yeah.
Brilliant. That's a fabulous way to end the talk, isn't it? Right, excellent. A round of applause, please.